The broadcast is now starting. All attendees are in listen-only mode.
Mhm. Mm. Okay, we are starting now our presentation, and first of all, good morning to the US people, and good afternoon to the European people. Speaking Gad Amir from VisiMix. I believe you know, and thank you very much. And it is our pleasure to be here with you in this presentation. The presentation will be provided by Dr. Ray Machado. And before it, I wanted to tell that all the audience are now in a mute mode, and if you have any question, send them through a question part of the presentation, and we shall give them to Ray Machado at the end of the presentation. Meanwhile, I may say that Ray Machado is the developer and the instruction of popular industrial short courses, fundamentals of scale up, which is teach part-time. He is currently employed by the Virtual Material Company and was for more than 31 years occupied in Air Product Company as a team leader of chemical engineering over there. And he has PhD in chemical engineering in the University of Wisconsin. He holds 20 patents and has collaborated on 15 publications. He is a member of the American Institute of Chemical Engineers and the American Chemical Society. And I would pass now the microphone to Dr. Ray Machado. Please, Ray, for you.
Well, it's a real pleasure to be with you this morning, this afternoon. I do apologize for the mishap last week. I had a small incident with my vehicle getting into work, so I decided to conduct this meeting from home so I have no more traffic complications. So I've been working many years with VisiMix and in lab reactors, and scaling processes up to 10, 20, 30 cubic meters in stirred tank reactors and also plug flow reactors and many other different types of technologies. But in that process, we had a lot of work that we needed to do. So let me talk about how VisiMix supported and helped us in developing many of our technologies. Go here to the next one. Okay. There we go. So one of the questions we want to answer before we do a scale up is a very simple one, which is where have we been, which is our lab reactor, and where are we going? many times we know where we want to go into our process tanks that we have that are existing for manufacturing specialty products, but we haven't necessarily done a sufficient job to characterize really how our laboratory has operated. We don't really always understand the specific details of the mixing performance of that lab reactor. And so one of the things I'd like to talk about today is how we can understand how VisiMix can be used to help characterize that lab reactor so that when we go to scale up, we know the parameters that we're trying to work with. We often are trying to make the lab and the plant reactor perform in the same way. But to do that, we really need to understand a little bit more about what is controlling our process, because many things can be a factor. It could be simple kinetics, which would involve maybe the rate of addition of a second reagent. It can be the temperature, which affects the overall kinetic rate constants. We could also have multi-phases that are involved in a process, such as a gas-liquid reaction for, say, an oxidation or a chlorination, or perhaps hydrogenation. We could have a solid-liquid process involving, say, something like a Grignard reaction, where we have metallic magnesium present, or we have, say, catalysts that are being used, or ion exchange resins that are in the process. We can have liquid-liquid processes where we're conducting an extraction or perhaps phase transfer catalysis. And so these are all the different types of situations that can arise. We can have simple blending processes where we're mixing materials, but also where we have for pH adjustments, or we have additional materials that are going in for making, say, a particular material. We can have heat transfer issues that are related to how effectively we can remove heat through the jacket of a reactor or perhaps a heat exchanger. And so these are all the various things that can control the process. And each one of those requires a different kind of scale-up parameter. It could be the rotation rate, for example, in our process. It could be the NJS, which is the rotation rate of just suspension for solids. It could be the heat transfer coefficient associated with our heat transfer processes. As things get larger, it gets harder to remove heat because the surfaces become a lot less. It could be the circulation time that's required, or it could be the power per unit volume for very fast reactions, as an example. The agitation intensity and the agitation equipment design can impact many of those fundamental processes. So, for example, blending and macro mixing, which involves just the overall pumping rate of the impeller, just tells us how well we're moving material through the reactor. We could have mass transfer issues where we have a power per unit volume, especially in two multi-phase processes where we have gas and liquid. We also would require impeller pumping flow rate as well. So we need to break up the bubbles and move them around. We could have a heat transfer. Typically that involves the impeller velocity and how well we're moving material past the heat transfer surfaces. We can have very fast reactions where local gradients of concentration can be impacted by how quickly and how effectively we move material. Impeller pumping flow rates, power per unit volume. Fast reactions become much more complicated because of the local reactions that can occur near a feed tube. We can have phase dispersion issues with solid liquid, gas liquid, which would involve power per unit volume, the kinetic energy of the materials involved, and the shear rates. And scale up is really about balancing these different process rates as they change with process size. The problem is that things change differently. So as you scale materials up, all of these variables are changing in different directions. And so it's best to find out which is the critical variable that is controlling your process and use that critical variable as your scale up. Now, it's important to understand a little bit about the mixing process. And so for just a simple mixing process where we have a low viscosity material that's operating in a turbulent flow, we can usually describe three different zones of mixing. At the very smallest scale, we have micro mixing. This is at the level of turbulence. This is where the turbulent eddies are involved, and they involve the viscosity, the density, and the power per unit volume that are in that local region. And that's important for the final reactions or as materials diffuse together. And this is especially critical when you have very fast reactions or you have things like neutralizations. Or perhaps you might have nucleations for the formation of crystals. Mesomixing is a slightly different region. That's where we have mixing at the scale of the feed tube and the impeller, where we're adding materials. The materials are swept through a wide region, but then eventually dissipate into the reactor as they become incorporated in the flow or as they react away. This involves where we put the feed tube, the rate that we add materials, the power per unit volume, and the impeller pumping rates. And finally, we have macro mixing. Now, this is the larger scale mixing phenomenon that occurs as materials are being pumped around and they're diluting the feeds as we add them to the reactor. And this is a function primarily of the feed rate and the impeller pumping rate. And so we'll use this sort of concepts as we go forward. So the first one is the overall blending and macro mixing. So typically we have a lab reactor and we're trying to identify, just about how quickly, how effectively are we actually blending or moving materials. Now, early in my experience, I had to work with a lot of very hazardous materials. And so in the lab reactor, it was not really possible to do some simple fundamental measurements. So I came up with a very simple technique, and the way this technique worked was like this. We would take the exact material that was in our reactor. In that reactor, we could have a polymer reaction, and we could have viscous materials. We had a heater that was at the top of the reactor, and we would turn the heater on for a specific amount of time with the agitator off. And then we would begin to turn the agitator on and the heater off, and you would see then the temperature in the vessel become more uniform over time. So at the beginning, you would have a high temperature at the top and a low temperature at the bottom, and this was your largest differential in the stratification of the reactor. And as the impeller agitated, the materials became more and more uniform. So here's an example here of what the delta T between the top and the bottom look like as a function of time. So here were the conditions of my reactor. It was 10 centimeters, and T represents the diameter of the tank. It was a marine impeller with a diameter of 6.9 centimeters. The fluid was approximately 1,000 centipoise and a density greater than 1. This was, I think, glycerol as an example. At 300 RPMs, we can see the delta T declining as we go with time, as the material becomes more uniform, and then at 400 and at 500. So the higher the agitation rate, the more quickly we achieve uniformity. If we plot that on a log scale, delta T over the delta T max as a function of time, we can get basically some straight lines, and the slope of those lines actually give us the mixing time constants for that particular agitator under those particular conditions. And so we can see that as we increase the RPM rate, this mixing time constant, which we can call basically a first order type process, increases corresponding to the agitation rate. Typically in mixing time, we talk about the mix time, which is typically the T99 or the T95, and that is the time required to achieve the desired form of uniformity, and that's typically proportional to 1 over the rotation rate for a given system. And so these kind of correlations can then be developed. And there's a list of those that you can find in the literature, or you can develop your own correlation for your lab reactor. In this example, we took a look at the VisiMix correlations, and here we have our uniformity from the previous experiment. Here's the actual trace from VisiMix, And over here, we did a comparison at 300, 400, and 500 RPMs. In this, basically, this is a laminar flow situation. And for the lab reactor, we received 90% uniformity in 220 seconds, and the VisiMix predicted 146. In the at 400, we had 86 and 92, and at 500, 53 and 64. And in the world of mixing, this is considered very, very good agreement because in mixing world, we're not looking for numbers that have three significant figures. You're typically looking for general order of magnitude within a factor of say 50%. So this represents a very efficient way to get your mixing numbers, was actually to use VisiMix. So once we established this ability with VisiMix, we no longer did all these experiments in the laboratory. We found that that wasn't as necessary once we had the VisiMix. So that really helped us as we continued our process development. Here's another example of what we did, which was to look at actually the rapid mixing time associated with a low viscosity material. We actually used water in this reactor, and I wanted to compare it to VisiMix. And so for this reaction, what we did was we added 60 cc's of ice water to the bottom of the reactor while the impeller was rotating. And as you added that 60 cc's, there's a rapid decline in the temperature overall, about a half a degree in the reactor. We measured this with a high-speed transducer, and then we modeled it with the blue curve. And we can basically compare that now, how fast we get to uniformity compared to VisiMix. So we measured a mixing time constant of 8 inverse minutes. VisiMix, which was 1 over the circulation time, gave us a slightly faster time constant, and that's really related to the difference between VisiMix using sort of a compositional approach, and we used a thermal approach. But overall, this is, I would consider, pretty good agreement. When we did estimation based on our impeller pumping rates, this is another way to look at the problem, where you calculate the pumping rate of the impeller over the reactor volume. This basically gives you a mixing time constant, and we put those values in. We estimated about 11 inverse minutes. And so you see here we can get different comparisons overall. The half-life using the thermal method was about 5 seconds, and the VisiMix was about 2 seconds. Cooling is very, so this really discusses our mixing time constants and how well we can get our uniformity within a macro mixing world. Heat transfer is another very critical component to scale up, and in fact, it's often one of the more limiting problems, because as vessels get larger and larger and larger, it becomes increasingly more difficult to get the surface area of the heat transfer to the vessel. If you only have a simple jacket, it's quite difficult. People will often put in recirculation heat exchangers in reactors to try to increase the overall heat transfer. But as the volumes get larger, the surface area gets smaller comparatively. So here's an example of a question we might ask, which is how long does it take to cool the reactor contents of glycerol, starting at 100 degrees C, and we want to get it down to 20 degrees C. And we can see that at different rotation rates with the constant jacket temperature of 10 degrees C, that if we're operating at 300 RPMs, it's 192 minutes, and if we're operating at 100 RPMs, it's 316 minutes. So the question then is, how do we characterize heat transfer in vessels? What's the best way to approach this problem? If we look at the heat transfer coefficients that we can get from the reactors, we can see that in the case of glycerin, it's quite complex, because as the reactor cools down, the viscosity of the material increases quite substantially. So we start off here at 100 degrees and we're at very low viscosities, and then as we cool it down, the viscosity increases, and so the heat transfer coefficients decrease correspondingly. So here's blue curve shows our glycerin viscosity as a function of temperature, and over here we see our heat transfer coefficients in red black and green corresponding to the different rotation rates. And so as the temperature goes down, the local heat transfer coefficients also decline. So how do we characterize systems like this? And how do we make sure that we can scale this type of a problem? Fortunately, the correlations for heat transfer are very well established. And the local internal heat transfer coefficient, which is given as the Nusselt number, and I think engineers are familiar with this. This gives us our overall heat transfer coefficient here. Can someone respond? Is everyone seeing my little arrow here? I think you can see the arrow that I'm using, or let me just try this here. The spotlight, yeah, there we go. So this Nusselt number then gives us this overall heat transfer coefficient. And when we plot this on a log scale versus the Reynolds number, we get a slope of 0.69. And that's exactly what the theory predicts at 2/3. So it's pretty close to the theory. So this is actually from our laboratory RC1 reactor, which was an MP10, approximately 1 liter vessel. And we've done this for many, many reactions and many vessels, and including large ones, and we get the same result. So if we follow this established correlation for heat transfer, we'll see that we follow it very well at different scales. And that's very, very important and very, very helpful to us, because that allows us to do a lot of things. So we did some predictions. This is the VisiMix predictions and experiments for heat transfer with an anchor impeller and glycerin in this RC1 MP10 glass lab reactor. So our jacket temperature here was 14 degrees, for example. In this first example, reactor temperature was at 25. The reactor fluid viscosity was at about 940 centipoise. We're in a laminar flow regime. The Reynolds number is quite low at 13. Our heat transfer coefficient that we actually measured by experiment was 58. And VisiMix predicted 59.5, so that's incredibly good agreement, and this is the heat removal rate under those conditions. At a slightly higher temperature of 31 in the jacket and 40 in the reactor, we had a fluid viscosity of a 274, still a laminar flow regime, and you can see extremely good agreement between the VisiMix and the experimental values. Likewise, at a slightly higher temperature where our viscosity is down to 89 degrees, we get a Reynolds number of 133, still in a laminar regime, but look at the good agreement we have with our heat transfer coefficients and the heat removal rates. So we found this to be a very effective tool in predicting heat transfer, and that's one of the more important scale-up ones, especially regarding issues associated with safety and making sure that your process is under thermal control, which is really one of your primary goals in any scale up, is to be under thermal control. Another important issue is understanding agitation and agitation and mechanical power input to the reactor to make sure that we can best describe the power per unit volume that goes in. This is very important for doing work for fast reactions, and knowing really what the capabilities of our mixer are in terms of the power input and making sure we don't burn out motors and the like. Now, it's fortunate that in the world of mixing, that a single curve can be used to describe the power performance of a given agitator. So here we see in this purple curve, the fluid foil agitator follows the following curve for all different scales. If we plot the power number versus the Reynolds number. Now, the power number is given as the actual power that was used in the process, okay, divided by the density times the rotation rate to the third power and the diameter of the impeller to the fifth power. So this number is established for different impellers and different geometries. We plot that on this left-hand axis. On the x-axis, we plot the Reynolds number, which is the rotation rate of the impeller times the diameter of the impeller squared over the viscosity. And this is a fundamental measurement in hydraulics that most chemical engineers are very familiar with. So what we see is that we get this sort of curve for that particular impeller. And every impeller has its own curve and for a given geometry. So here's an example of a Rushton turbine with and without baffles, and so knowing these well-established curves gives us a lot of information. Now there's two regions that are the most important. One is in the laminar region, we know that the power number is inverse to the Reynolds number. That's a very important observation. And likewise, in the turbulent regime, we find out that the power number is actually a constant as we go more and more turbulent. Turbulence in stirred tank reactors typically occurs somewhere near 2,000, Reynolds number of around 2,000. That does depend, however, on whether or not you have baffles, but certainly between 2,000 and 10,000, we go into a turbulent regime. In between is a transition regime, which is a lot more difficult to characterize. This is somewhere between the laminar flow and the turbulent regime. Now, one of the general problems that can happen in a plant and for scale up, but this is kind of important to understand, is that sometimes a lab reactor can operate in a transition or laminar flow regime, and the plant reactor can operate in a turbulent flow regime. Now, why that's important is because the different flow regimes require different types of impellers. So it is possible that when you're doing a scale up, your lab reactor might require a different impeller than your full plant. So this means that having geometric similarity between the lab reactor and the plant reactor is not really very important when this occurs. So here you may have to have different impellers for different situations. And that's important to recognize. So doing this first calculation, and as you can see, the most important variable to understand where you're at is really your viscosity. So getting viscosity measurements are very important. Of course, if you're using low viscosity materials, it's not a problem, but when you start doing polymerizations or materials that are more viscous, then you can really you need to really understand the influence of viscosity. We had characterization for a Mettler-Toledo AP015.5 reactor, a small reactor. The volume of it is, I think, about 500 cc's. And we wanted to understand a little bit more about its power performance. And so we actually did measurements on this reactor. This is a nice system because it really covers a variety of regimes. This simple paddle design and impellers allows you to operate one reactor from low to high viscosities all in one system. So we actually did the measurements. We measured the power using torque meters, and we plotted this for different impellers. So in this particular case, we had the red curve represents 3 impellers having a slightly higher power. We can see here we have the inverse to the Reynolds number in this regime by plotting the power number versus the Reynolds number, and we become constant over in this regime. When we have 2 impellers, we go the blue curve, and 1 impeller is the green curve. And we use this very simple model, which really derives from well-known literature type of correlations, and we developed this little correlation for that reactor and understanding the power. So now if we run a reaction and we know the viscosity, we can understand what the power put into that reaction was. We also did macro mixing correlations based on thermal uniformity for this AP01 reactor, and we also developed a model for that. And so here we have the T95, which is the time to achieve 95% uniformity times the rotation rate, gives us a dimensionless number because this is rotation per time and this is time. So basically you can think of this as actually the number of rotations. And this here is the Reynolds number. And this follows a very traditional type of curve that you would see for in large scale industrial reactors. It follows a similar trend even in the lab reactors as well. And so here we have the different equations for those different situations based upon this correlation. So I wanted to compare this, what we see with the VisiMix. So let's take a look here at a couple of things. Well, we'll start with the power numbers. That's probably the easiest at this point. So in the power numbers, here's the VisiMix power number calculation, and here's the experimental one. Now for the VisiMix, what you often have to do is perhaps a modification. They don't have a flag baffle in VisiMix. However, I basically modeled it as the same surface area as the flag baffle, which is the way you would want to do things. So sometimes in VisiMix, we have to make an adjustment that makes engineering sense because it doesn't have exactly the same internals. And so here's the power numbers at 900 RPMs. You can see very good agreement, 300 RPMs with one baffle. And here we have two baffles in this particular case, or excuse me, two impellers. And you can see very good agreement between the power numbers. And then finally, we have three impellers here. We see also very good agreement, 24 and 22 basically, 71 and 63. So this is excellent agreement in power numbers, and it's certainly a lot easier to do a 5-second estimation in VisiMix versus a 5-hour experiment that you have to set up. So we are very satisfied with this level of correlation, and really because of that, we didn't need to do any more laboratory experiments to get power numbers. We did take a look also at the mixing time constants associated with that. And for VisiMix, we looked at two different numbers, one over the circulation rate and the K-mix based upon the composition, which can be achieved by measuring the composition changes over time. And we compared that to our thermal method, and you can see the thermal method really lies in between the two. And we felt that we had good basic overall agreement between the two. So for example, it's two impellers, we're measuring 1 over circulation rate of 1.39. We measured 0.044, and the VisiMix for the composition was 0.0074. So we really are measuring our macro mixing times in the right region. And we want to note that the thermal uniformity in liquids is achieved a little bit more efficiently than composition because of the thermal diffusivity. And so uniformity explains in part what some of the differences. So if we had used a compositional method, we would have probably gotten different numbers. But we were very satisfied that we get the right macro mixing times with the VisiMix software. So we didn't have to do any more of these calculations. Another very important variable in scale-up is gas-liquid mass transfer. In my former work with Air Products, we basically provided support for hydrogenation to many customers, and so as we sold hydrogen or oxygen to them for various reactions. And all these experiments, by the way, I want to just give a little explanation here. I have a separate company at the request of Air Products at the time because they didn't want me to be teaching this class at conferences and whatnot under Air Products guys, so they asked me to sort of separate myself when I taught the course. And all the materials that I teach are all general purpose information. There's nothing that's secret to any companies. This is all just sort of generic stuff. And all these measurements were actually made in my home laboratory where I had a mixing lab. So I didn't use my corporate resources for this. This was used on my own, and it was done really for educational purposes. And originally I taught this course at Lehigh University. So that's sort of a little bit of the background as to why I teach this as a separate way. It was really at the request of the company. And they were very fine with this. And in fact, I teach the course internally, and I still have taught it to people at Air Products at the time. Okay, anyway, that being said, so understanding mass transfer is very important. So what's typically done in laboratory reactors is we use a hollow shaft impeller that basically recirculates gas. It draws gas in through the top here. Let me show you with this marker. what goes on. So in this vessel, we agitate. We have a baffle. We have different heaters and elements that are associated with the RC1 type equipment, the MP10 reactor in this particular case. This is a hollow shafted impeller. As it rotates, what happens is at the tip, the pressure goes down significantly based upon Bernoulli's principle. As you know, the faster you go in a given system, the lower the pressure, why airplanes fly and things like that. So when that happens, it draws gas in through this hollow shaft and distributes the gas accordingly. We measured the gas flow. I developed a little method to measure gas flow from this impeller at a function of RPMs and different liquid levels. So here we have 300 to 800 mLs, and here we measure the gas flow rate given in these curves here. So here's a particular experiment that you would do to measure mass transfer. So we now know from the previous work here the gas flow rates. Now we're going to measure the mass transfer coefficient. So in this particular example, we start with a very low rotation rate at 200 RPMs, and then we quickly ramp it up to 1,000 RPMs. Now, if we have a closed vessel and we have pressure in the vessel, let's see what happens. So we see that at time 0, we begin this ramp up here in the RPMs, and all of a sudden we see a decline here in the pressure in the reactor. And that's because as this occurs, we're getting absorption of gas into the liquid. Basically, gas is dissolving. And as the gas dissolves, the pressure goes down, and we can use this decline in pressure to estimate the overall mass transfer coefficient, or how efficiently at a given RPM rate we can absorb gas into the liquid. So as we're doing, say, hydrogenation, we need to constantly replenish the gas in the liquid phase because it gets consumed by the chemical reaction. And we don't want to starve our catalyst of hydrogen or of oxygen in the case of an oxidation. And so you want to maintain a very high level of replenishment or high mass transfer rate. We can think of this as a first order process of gas from the gas phase going to the liquid phase, and we can think of the mass transfer coefficient basically as a kind of a rate constant in our process here. And that will be given as the KLA. That's the rate constant. Now that's a function of our agitation intensity and the gas flow rate, as we saw earlier. And then the driving force is the saturation concentration at the interface minus what's in the actual bulk phase. And that's really our overall driving force. So this is the rate constant associated with that process. A little bit of manipulation generates the following equation. If we can plot the natural log of the pressure minus the final pressure versus over the maximum initial pressure from the charge of gas into the headspace minus the final pressure, and we compare that to this constant here versus time, and we plot this on a log scale. As you can see, you'll see that all of a sudden we see this pressure following a linear profile of log versus time, and that allows us to measure from that slope the overall mass transfer coefficient. So this is an important way of determining the capability of our lab reactor to replenish gas, and we'll see how that helps us in the future for getting information on scale up. So we can adjust our lab reactor, for example, to match various types of mass transfer coefficients that we might need in our scale up. Here I have the mass transfer coefficient that we got from all these experiments compared to the RPM, and this is at different liquid levels. So let's take a look at comparing this to what we predict in VisiMix. Okay, so over here we have all the particular details of the experiment. This was done at 140 C for this particular experiment. It was about 1 liter of material, a surface tension 26 dynes, viscosity 0.25 centipoise, the density about 930 grams per liter. So this was the real experimental material that we were using. We had the standard gassing impeller. This is for the HP60 high pressure reactor. and the diameter of the vessel was 10 centimeters. From our previous correlations of our gas flow rate, we knew that we had the following superficial velocities. Superficial velocity, for those of you, I think you might be well versed in this. This is basically the volume of the gas flow rate divided by the overall diameter of the vessel. And so, I mean, overall surface area of the vessel. So you take the cross-sectional area of the vessel and you divide that into the overall the gas flow rate to give you the superficial velocities. So here we have at different RPMs, the increasing superficial velocities. We have agitator power that we actually measured, and we have the actual mass transfer coefficients that we measured in the laboratory experiment. For the VisiMix, we didn't have exactly this gassing impeller, so we chose to look at it under two conditions. One was to match the power, and the other one was to actually use the blade width itself of 10 millimeters. So we chose two different approaches, matching the power and then matching the diameter, the actual geometry of the vessel itself, okay? When we did that, we get basically two different regimes. And you can see that using those different methods for getting heat mass transfer coefficients here, our values here are right in between. So we at 1400 RPMs, 0.42, here we have 0.33 and 0.87. At 0.33 here at 1200 RPMs, 0.16 and 0.40. And here at 1000 RPMs, 0.23, and that's very close to these values. As the RPMs go down and the gas flow rates are pretty low, the correlation was not quite as good, but still within an order of magnitude, not a bad fit overall. So here's some summary of what we see there. We see basically the measurement of our vortex. We measured 2.5 centimeters. VisiMix gives us 2.1. And if you use the actual impeller width here, which is a little bit wider, you get 3.6. Our mass transfer coefficient measure was 0.42, and here we have 0.33 and 0.87. And this also gives us our gas holdup, our solder mean diameter, circulation rates, etc. So we get a lot more information which we can use for our scale up. But sometimes in the VisiMix we have to bracket things. Not everything is a perfect single number. Sometimes we have to look at things differently, approach the problem from a couple of different angles, and help us to sort of like guide the regions that we're in. And that's an important rule of scale up. There isn't necessarily a single number that gives us the answer. Sometimes we have to bracket our problem, and this is an example of how we can bracket the problem and look at it. And so you can see that certainly we're going to be somewhere in between these. Scaling up mass transfer coefficients can be quite a challenge, and let me describe how this was done. So how do we scale up all this? We have the mass transfer coefficient. Here's a slightly different approach. Which we're going to do is we're going to adjust the pressure in the lab reactor to achieve the same results as the plant reactor. So this is actually a scale down activity and see how we can measure mass transfer coefficients in a very large vessel without doing these experiments in the vessel. So we have the plant and lab raw materials and catalysts are from the same lots. This is very, very important, that we have materials that are from the same exact lots for our experiments. Mixing in the lab reactor was measured to be very high. So we're going to run our lab reactor at very high mass transfer coefficients. And this mass transfer coefficient is so fast that it's compared to the reaction that our lab bulk concentration is essentially equal to the saturation. So having measured our mass transfer coefficients, we know how to get this to occur. Then the lab reactor pressure is adjusted to match the plant rate profile. So there was a plant reaction that was done, and in that plant reactor, we measured the pressure, the uptake of hydrogen, in the reactor, and we know, of course, the temperature in the reactor. We then programmed our lab reactor to exactly match the temperature profiles of the plant. So we matched the temperature profiles of the plant, and then we did something very interesting. So we adjusted the lab reactor to give an equivalent volumetric rate as the plant. So when the plant was at 800 pounds of pressure, we found that we could get the same result in the lab when we ran it at 700 pounds. So sometimes this is what we have to do. We have to adjust the concentrations in our lab reactor to match the plant reactor. Now, knowing this, we can use this information in a very unique way. So we know that that if the plant is operating at 800 RPMs, that pressure in their bulk phase is equivalent to the saturation pressure of the lab reactor at 700 pounds pressure, because we ran the lab reactor at very high mass transfer coefficients. So that being said, we can then put in the rate of the plant reactor. We know the hydrogen saturation at the plant, which was 800 pounds pressure at saturation, but we also know that it was operating when the lab reactor was at 700 pounds saturation. So here we have our lab and our plant reactor. We put in the data as I described, and of course in the course we go into much more detail of how we do this. I'm just really giving you an overview. So the plant reactor at 800 is equivalent to the lab reactor at 700. We measured from our scale down 0.52 and from our VisiMix 0.6062. So it's very good matching of the mass transfer coefficients. And this also allowed us to do our scale up. Now that we've scaled down the plant reactor, we can do a lot of things with that data. For liquid suspension, I'm going to move a little quicker now to get past the liquid suspension, but we also did things by putting conductivity probes at the bottom of our lab reactor. We measure basically the conductivity as we increase the rotation rate, and we measure that here, and then we observe at the bottom when we see suspension off the bottom. So using a conductivity method, we can get this information of when materials are off the bottom. Generally, for solid or chemical reactions, we just want to keep things off of the bottom of our vessel. It's not necessarily important that everything is uniform in a chemical reaction unless we're drawing material off. But if we're not doing that, it's most important to get it off the bottom. That's really what we worry about, especially for things like Grignard reactions or materials that are very heavy, adding zinc, for example, as a reagent to our vessels, things like that. Zinc powders, copper powders, things that might be difficult to remove from the bottom or move from the bottom. The NJS is the rotation of just suspension. It follows the correlation for just suspension, follows the Zwittering correlation, which involves the fraction of solids in the material, the gravitational constant, the difference between the density of the material you're suspending and the density of the liquid, the density of the liquid itself, the size of the particle, the kinematic viscosity in the liquid, and a constant associated with that vessel. So this must be determined empirically for the lab reactors and for the plant reactors. So I compared this to VisiMix, and here I was able to calculate the material off the bottom from my conductivity. VisiMix was in red, and then my experiments were in blue. And so you can see that at the point of just suspension, I actually get a pretty good correlation. We're at about 12% solids, where at the average in the vessel was about 6%. That's the bulk. If you take all the solids divided by the liquid volume and mass, you get about 6%. But you can see that near the point of just suspension, I had good correlation. I did find that it was a little bit more difficult to get the solid suspension to match the VisiMix if you didn't get the geometry exactly correct. If we assume the composition and the physical properties are the same in the lab and the plant, our scale-up follows the following very simple scale-up correlation, where the just suspension of the plant compared to the just suspension and rotation rate of the lab are given as the following ratios, which is the constants for the plant versus the constant for the lab. These are empirical constants that are determined for each vessel, and divided and multiplied by the difference in the diameter of the impellers. That's assuming that there's a similar type of impeller. So in the scale up using VisiMix, we have to match the solids concentration profiles between the lab and the plant, especially at the bottom of the reactor. And we need to ensure that the particle-particle energy in the plant reactor is less than the lab reactor. So sometimes in the scale up in the plant, we might have to have lower solids. That's very important. And I wanted to note that I was not as successful in matching the solid holdup between the VisiMix and lab unless the exact geometries in the lab reactor was matched with the VisiMix reactor geometries. When I got the exact geometries without any kind of modification, then I got a much better correlation. Mixing regimes we visualize as micro-mixing occurs in a very small local area. Meso-mixing is swept out region, and macro-mixing is really occurring in the overall volume. I think many of you have seen this type of a process when you do a pH titration, for example. Early on in the pH titration, what we see is a very rapid reaction at the beginning and a very local region. And as the titration continues, eventually you see a color change distributed over a larger volume. So actually, in a titration, we go through all these different mixing regimes simultaneously. Not simultaneously, but in sequence, starting off small and then winding up over a wider range. So many of you have actually seen this in real life when you've done titrations. For different types of reactions and different types of mixing regimes, we have different sorts of rules that occur. So if we start with the simplest is macro mixing, really the dependency of a process on macro mixing really is about the feed rate. So the macro mixing, so for example, if we have a macro mixing control, the only thing that we can then control is the feed rate, and we want to keep this constant, which is the rotation rate times the diameter cubed divided by the feed rate. And what that is basically gives us a kind of a dilution process that goes on, where the feed coming into the reactor is divided into the rotation rate times d cubed. This is the pumping rate of the impeller. So this is a relationship between the pumping rate of the impeller and the feed rate, and that's a dimensionless quantity. And that really is what controls is when you have macro mixing control. When you have micro mixing control up here, the feed tube location is very important. You know why? You can see that. The feed tube location determines what the local intensity is. And so if you're far away, it's a bigger zone. If it's closer, it's a smaller zone. And that really depends upon the viscosity of the solution and the feed tube location. And the rule of thumb there is power per unit volume, because power per unit volume really determines the local area of turbulence that feed tube is located. Macro mixing is occurring over a much larger range. A more difficult region to control is the meso-mixing regime here, which depends on feed tube location, your feed rate, and the number of feed points. And the rule of thumb guideline there is quite more complex, which involves n to the fourth d cubed over the feed rate and the number of feed locations. In the short course, we go over a lot more details associated with this, but you can see it depends on a lot more variables. I'm going to show you an interesting example here, which I compared to VisiMix, and let me describe this because this is a very fun and interesting experiment that I did. So into this reactor, I have put, let me get my spotlight here. Into these reactors, I have a solution of thiosulfate. And the thiosulfate solution will then neutralize the iodine. It's an oxidation reduction reaction. So I'm going to oxidize the thiosulfate, the sulfate, and when that happens, and I have a starch indicator in here. And so when iodine sees starch, we know what happens. Iodine will turn yellow. And so in our process chemistry, when we see a yellow color, that's really the reaction of the iodine with the final starch. If we react the thiosulfate with the iodine, that becomes a clear solution and gives us the iodide and then the sulfate solution. Now, if the iodine reacts with starch, then we see this black color here. So iodine is yellow, the reaction of starch is black, and the reaction of thiosulfate with the iodine starch reaction then also turns clear. So we can see the different colors give an indication of what's going on in the reactor. So in VisiMix, I wanted to do a prediction between the maximum difference of the thiosulfate solution during this oxidation reduction chemistry process. And so I then calculated here the maximum difference of A in the reactor, which is thiosulfate. What's the maximum difference as a function of two different RPM rates and over an addition time of about 50 seconds. And so let's take a look at this. Now this is going to be a video, so I'm just going to stop this video at a couple of different points. So I know you won't be able to see the video because it's of the time in the as we go forward, but I'm going to stop it at a couple of points here that we can then take a quick look at. Okay, so we can see here, if you look very closely, you'll see some yellow up here by this 200 RPMs, and you can see the yellow coming through, and that is iodine solution that is just unreactive with anything, but you begin to see a little bit of a black cloud here as iodine is reacting also with the starch solution. So it's not able to completely be consumed, and so some starch is being formed, and we can see that this is the point where we see VisiMix shows pretty much a maximum in terms of the differential. So at some point in here, we have we have a 10% lower amount of thiosulfate than at another point over here that we chose in the VisiMix correlation. Okay. We'll continue in the process. And as the process continues, what is actually happening is we're consuming the thiosulfate. So our reaction is actually changing. Let me stop here. You should be able to see. So now at around 25 seconds, we see the yellow plume over here at 200 RPMs, and we see a gray cloud. But at 800 RPMs, we see just a very small amount of yellow iodine coming in because that iodine is reacting very, very rapidly. There's almost no cloud of starch reaction. So this is being very efficiently reacted with the thiosulfate solution and shows a much lower differential in the reactor because of the very rapid reaction that's occurring here. And that's because of the higher RPM and the greater mixing intensity at this region over here. So let's continue. As we continue, we see that you go a little bit further to about 45 seconds. Okay, at 45 seconds, I think we can see now a very large cloud of the iodine reaction with the starch solution, and that's because we've consumed a lot of the thiosulfate solution already. So as the reaction proceeds, the kinetics change, and we start to see more influence of mesomixing. We're beginning to see a region that's much larger than the small region here. In the higher RPM range, we see still a little cloud of the iodine reaction with the starch, which we consider, say, an unwanted reaction. And so that's beginning to occur here, but still much lower than here because of the greater mixing intensity associated here. And that's really also predicted in the VisiMix model as well. And then finally, we get to the end of the addition. And what's important here is we've just about consumed all of our thiosulfate. And so now in this reaction, macro mixing is becoming an important variable. So at the end of the reaction, macro mixing is a little more important than the micro mixing. And we see over here, we're probably in a more of a meso-mixing regime. Looks very similar to a titration that you might see. Still a little bit of the yellow, the black cloud of the starch reaction, and then eventually this goes away as the starch reaction completes. And then finally, the process is completed. We can plot then the overall reaction time, which I measured by the disappearance of I went frame by frame in the videos, the disappearance versus the 95% mixing time, and I see a pretty good correlation that my reaction time is really related very much to my overall macro mixing time. And that's a good estimate for this reactor. So what have we learned? VisiMix predictions and lab reactor mixing measurements agree well with reactor geometries match and physical properties are known. So we really get a pretty good correlation, and we were very satisfied in now using VisiMix as a way to characterize our lab reactors. If lab reactor geometries do not match the catalog of available geometries in VisiMix, geometric approximations can be made. And so for the power and heat transfer, the errors really are insignificant. So for doing power calculations and heat transfer, VisiMix can be very easily used by doing modifications to the geometries as necessary, and we found that to be very convenient. For solid suspension, it's a little trickier, and for phase separation and circulation, a more detailed mixing data for the lab reactor is necessary to adjust the approximations, and validations may be necessary. So for solid suspensions, it's a bit trickier, and you need to take a little bit more time in doing that. The limitations of lab mixing characterization methods, such as thermal tracing, must be considered when using them for scale-up or matching more detailed VisiMix models. We're very convinced that we'd rather use the VisiMix models than the thermal methods in many of our scale-up methods. So we've been very satisfied with that. Some very simple practical advice for those of you who have to go do scale-up tomorrow morning in your plant reactors, which is, you know, if you get bad results in your semi-batch process, you can always slow down your feed rates so that your feed rates become adjusted according to your mixing capabilities. You can dilute your feed concentrations, which then dilute at the feed point to keep you in a regime where you don't have a high concentration gradients. You should increase your mixing intensity so that basically your dilution rates are a lot faster. And of course, you can always lower the temperature a bit so your kinetics slow down so you don't wind up with reactions that are occurring too quickly. So these are some of the things that you can do, but of course, lowering temperature also increases viscosity, so you know you have to be a little bit careful with all these different things. I think these notes will be available online through seeing this course again. If you have questions, you can ask me. Here's just a simple abstract. But something that I think is important to show you is these pictures over here. So this was me giving a course in 2003, and you can see a slightly more volume. I occupied a bit more volume in those days. I'm a little bit thinner in 2018, and now that I live in Arizona, spend a lot of time in the mountains, hiking and backpacking and doing that sort of thing. So there's been, you know, a change in the overall process from here to here, a little bit more action and a little less mass in the process. Okay, great. So it's been a real pleasure to talk to you, and I'll take any questions.
One moment, let's try to pass it on. No. Do you have the question that I pass you, Ray?
Sure. Go ahead. What's the question?
I try to pass it to you, but the question here is, does this presentation include our worst case study for 1,000-liter tank?
Worst case study.
Mm-hmm.
So for a 1,000-liter tank, let me just say this. I would be very comfortable with the VisiMix calculations at that scale, and scaling up from a 1-liter reactor to 1,000 liters is not a difficult process. I would probably start with a 1-liter type of reaction vessel. I don't know if that answers the question at all, but like I had discussed earlier, I would look at different assumptions that would give you sort of a best and a worst case for a mixing situation. I would always frame a problem between two extremes if I could. That would be just a rule of thumb to bracket your problem and your assumptions. So if you were doing, say, mixing calculations, I would base it on the geometry and also the power per unit volume, for example, as I showed you with the gas mass transfer problem, or I would bracket it in different ways. I don't know if that answers your question. If you want a more detail, you can send me your question in more detail, okay, and I can answer it. And you send it in an email.
Great, Ray. And thank you very much, Ray, for this presentation. It was really great, and I can tell all the audience that we are going to send you the recording of this presentation. And if you shall have any additional question, don't hesitate, send the question to us, or you can send it directly to Ray, and we shall, of course, share with you the answers. And in the meantime, I wish you a wonderful day. Thank you very much. And I can even tell you that now it is holidays here in Israel. It is Hanukkah holidays. So I wish you Hanukkah Sameach, Happy Hanukkah from us, from Israel, to all the audience. Thank you very much, and we shall be in touch. Thank you, Ray. Thank you, Ray, again.
Thank you. Okay. Bye-bye.
Okay. Bye. Bye.